Okay, any question before the class? Okay, let's get started. We are in the middle of talking about memory access instructions. Last time, single register transfer, right? We'll talk about these two today. Okay, single register transfer. So last time, we talk about one word, data transfer. Right? One word, right? One word. Word is determined based on architecture, CPU architecture, right? We are talking about 32-bit architecture, right? 32-bit CPU architecture. So where, word size, one word is 32-bit, 4 byte, right? So in 32-bit CPU, data path, right? Data path is based on 32-bit, everything, right? The path data is traveling through, right? It is taking two 32-bit data, generate 32-bit, right? And that is because register file is also 32-bit in size, right? You have 16 registers in ARM, and each register is 32-bit in size, right? So that 32-bit. So that is determined register size, right? This register size, that is determined based on architecture, right? And that is also data path, right? Data is traveling. So you are reading 32-bit, 32-bit, and then do some processing, then output, store back, right? So that is why, the memory access, right? When you do memory access, sometimes you want to read. So depending on, right? If you think about a data type in C language, data types, right? Like int, short, right? Int, that is 32-bit, right? Short, 16-bit. Cha, character, right? 8-bit, 1 byte. So depending on the data type you use, sometimes you read one word, right? That is 4 byte, and place into register. So for that purpose, you use LDR instruction, right? And opposite, right? Store, right? Store STR, right? For short, we have some problem, right? 2 byte read, 2 byte. Short is 2 byte, right? 2 byte read, but the problem is register. Each register is 4 byte in size. So we have some problem, size mismatch. 2 byte, 4 byte. What do you have to do, right? So register, say R2. Okay, so you are placing this one, and that 2 byte is always placed in LS position, least significant lower position. Okay, lower position. And then upper 16-bit. Hardware is doing sign extension or zero extension, right? Depending on instructions you use, right? LDR H. Then CPU will do zero extension, fill zeros, right? LDR SH, signed, right? Signed half word. Last one, right? Last one. Signed half word. CPU will do what? Sign extension, right? Depending on the data, depending on the MSB, most significant bit, then do sign extension, right? 0 or 1, depending on this bit. So in this way, you don't change the meaning of this data, right? So think about this one is negative number, right? This one is negative number. So minus something, minus 2, for example. Then MSB will be 1, according to 2's complement notation. So in this case, you have to use this instruction, signed, because you think of it as signed half word, signed number, right? Signed number. So then that upper 16-bit will be filled with all ones, so that the data will be still -2, right? This whole 4 byte. Right? Think about that. Okay, think about that. So zero extension, right? And sign extension, very important mechanism, right? Very important hardware mechanism that is supported by instructions. And if you use this one, then CPU will do zero extension, this one sign extension. Hardware is prepared. Hardware is ready for that, the extension operation. Okay, that is one. Probably I don't have to, explain this, right? You are reading from this location, okay, and place it here. This one, R1 plus 16 position. Right? Read from this location, place into R0. Okay. So next one, opposite, right? R0 goes to store to the location, Okay. This one is a little bit. This one is a different flavor of single register transfer. Okay, we are still talking about single register transfer, but different flavor. Okay, so look at this. So we are talking about these instructions. Right? It's better to use examples, right? LDR, memory read. So you've seen this code here, right? This code, LDR. Okay, but take a look at this. Looks very similar, but you have exclamation mark at the end. Okay, and looks similar, but square bracket is here. Okay, R1, but it is enclosing R1 and 4, so different flavor. Okay, Mingyu, can you please read this one?
어떤 식으로 읽어야 될까요? 그냥 순서대로 이렇게 가로로
Yes.
읽으면.
Yes. I want to take some break because I don't want to lose my voice. That is why.
offset, rn plus offset, and
This one. You don't have to read, everything. Only this one. This one.
okay. Addressing mode, offset addressing, and pre-indexed addressing, and post-indexed addressing.
Okay, thanks. This one. This is operation simple, right? R1 plus 4 location. Okay, let me show you animation. Okay, better to use this one. So let's go through this example. Okay, so this instruction very simple. R1 we are assuming this before status, and we want to know after, right? So R1 plus 4 position. R1 contains 9, right? 90,000 in hex. So from 90,004, okay, from the memory location, okay, then location, you place this one to R0, okay. So result is R0 register will have this value, okay, because you are reading from this location, okay. And this instruction, pre-indexed addressing, okay, pre-indexed meaning. Think about the meaning of this terminology, pre-indexed. Before you access, right? Before you access memory, do this addition. Same operation, right? So before you access memory, right? Do this addition. So same thing. Before you access memory, you have to do R1 plus 4. Okay, and read from the location. So you end up reading same data. But what is the meaning? What is the difference between these two? You have exclamation mark, meaning after accessing memory, R1, this base register, will be updated to R1 plus 4. Okay, so after R0 contains same value, okay, but R1, this base register, is updated to that number. Okay, so pre-indexed means before you access memory, do this addition first. Okay, do this addition first, then access memory, and exclamation update this base register. So one instruction is doing two operations, right? So hardware operation, right? LDR, R0, R1, and you have exclamation mark. So first operation is you are reading from R1 plus 4 position. The second hardware operation, R1 register will be updated with this addition outcome, right? So two operation will be done by hardware. Right? Okay, and the last one, post-indexed. So after, right? Post is after. Okay. So do memory access first. Okay, memory access first, and do this addition next. Okay, after, right? So read from this location R1. R1 contains this 9. Okay, 900,000. So read from this location. So R0 will have this value 01, 01, 01. Okay, and then base register is also updated like this. Okay, 01, 01, and like this. Okay, so you see the difference, right? The location is different, right? So R1, R0 from this location. Okay, okay, you have a read from this location first, then after reading from after post, right? After reading from memory, update this base register with this one. Okay, do this addition next after, right? It's a little bit confusing, right? The question is, when do you want to use this kind of instruction? Okay, so application example. So think about this simple example. You have an array of 100 element, okay? And then you want to add all the element in this array to this, sum, for example. So 4, right? I 0, I plus plus. Then you want to add everything. Sum plus sum A, I. Think about this code, right? You want to add all the element in this array, right? And place into sum, right? Then if you write this code, this array, if you compile this, array is placed in all the element in this array is placed in consecutive memory locations, right? A0 first here, A1, A2, and so on, right? A99. So assume that R1 register contains the location of the first data. So then you want to read, you want to, to add this data, you have to read first, right? You want to use, in this case, what? LDR, which one do you have to use? LDR, R0 probably, okay, place it here, R1, okay, read from this location first. Don't do this addition first, right? And plus 4, because integer, right? So 4 byte each. Then this instruction will do this operation, right? Read from this location. Read the first data. and place it to R0 register. Second, this base register will be incremented by hardware. That means it is pointing the next location, right? So without this post indexed addressing, you have to use two instructions, right, to implement this, right? So first one, LDR R0 R1, then add, right? R1. So instead of using these two instructions, you can, this one instruction will do the same thing. Okay, so code size would be smaller, okay, compared to this. Does it make sense? So if you check out this example code you set up in IDE, so look at this one, LDR, right? Okay. LDR, that is post-indexed single memory access, right? Post-indexed. Read from this location. What is the location? So you initialized R0 with the location, right? Location of first data. This is a label, right? This label is location. Memory location, right? Memory location. So initialized R0 register with the location of first data, R1, and then instruction, LDR instruction is reading this first data, right? 1. And then R0 register will be incremented by 4. So R0 register next time is pointing that location, okay, this location. So let me show you. Let me turn on the board. Okay, then compile just in case. Okay, and download it. Debug. So I don't have to show up the board, but camera is not on. Okay, no problem. Why is that? Okay. Okay, it's working. Okay, so I don't have to show the board because nothing will happen on board, right? So anyway, so it stopped here, and you need to check out probably registers, right? Okay, so run 5, then R0 register contains that value 100 9E0. Okay, so let me remove this. So there's a memory tab. Using this tab, you can dump memory content, main memory content, right? This memory, we have a memory located mounted here too. Okay, that is Zinc 7000. These two chips do these two main memory. Okay, so you want to dump, right? Read from their location. Okay, so okay, check out this. Then so 1, 2, 3, 4, 5, that data, right? Data we placed. Okay, data is placed at the locations. Okay, at those locations. So what do you expect if I press F5? Oh, no, not this one. Okay, so let me do this F5 and R2 16. What if I press F5 one more time? What do you expect? are reading from R0, right? So reading the data, okay, first data. So R3 will have 1. Then R0 register is incremented by 4. So it will be 9E4, right? 9E0 to 9E4. Okay, 9E0 to 9E4. Okay, that is our expectation. So let me press F5. Okay, so 9E4 and R3 register contains 1. So you just read, right? One data, okay, first data, and then increment it. Okay. So again, play with this code, right? Play with this code. It has memory access instructions, branch instruction, data processing instruction, okay, everything. Okay, so there is one. Any question before we move on? Okay, next one. Okay. Then now, second category of memory access instructions, multiple register transfer. Okay. So that is a format. Okay. So LDM, load multiple, memory read, right? But you want to read multiple data, not just one, word, multiple data and place into registers. Okay. So those instructions are provided for performance reason, right? One instruction is reading, multiple data, right? So for performance reason, right? Instead of using single data transfer instructions, you can use just one. Okay, you can just use one memory access. For example, register file, right? You have R3, R4, R5, R6. So with one instruction, you can read, 4 words in memory, 4 words in memory, and place into here. So using LDM. Opposite you can do, STM, store multiple, right? That is basic operation, right? So load multiple, store multiple. Some addressing mode you need to specify, okay? Some suffix. So like, because when you read, right? Okay, let's first read PowerPoint and get to explain. Okay. Someone, can you please? These two, bullet.
LDM loads general purpose registers from sequential memory locations. STM stores general purpose registers to sequential memory locations.
Okay, thanks. LDM, STM. Look at this instruction encoding format. Okay, so here, operation code, LDM operation code for STM, right? So difference is, I think this one, 20 bit, 1 for LDM and STM 0. So CPU, right? Hardware, take a look at this one and also this one. Okay, so then figure out, okay, this is multiple load instruction. Okay, these are multiple store instructions. So important thing is this one, register list. In CPU, you have 16. How many? 16 registers. 16 registers. That is why you have 16 bits here encoding. Okay, so each one is corresponding to in one register. Okay, each one. The first one, first bit is corresponding to R0. R0, Second bit is corresponding to R1 and so on. The last one R15. Okay, so 16. Again, the first bit R0 register. Okay, so in this case, LDM, you want to place, this bit is set to 1, then you want to read the first data and place into R0. Okay, so 16. So, anything is possible, right? Anything is possible. Very simple instruction format. And then syntax first, it's because it's a little bit, complicated. Jisung, can you please?
In multiple data transfer, the register list is given in a curly brackets. It doesn't matter which order you specify the registers in: lowest register, lowest memory location, and highest register, highest memory location. A useful shorthand is dash. It specifies the beginning and end of registers.
Okay, thanks. Important thing, syntax, right? So multiple data transfer. So in this curly bracket, inside this curly bracket, you have to specify which register you want to load data to or store data from. Okay, load data to. Okay, like this. So in this case, store multiple, right? Store multiple STM. You are doing what? R0, R1 register, these two. Okay, place into memory. And exclamation mark. Okay, R13. Okay, R13 is the location. So base location. R13 register is pointing the base location. Okay, from this location. Okay, this base. And then one more thing. Exclamation is meaning right back. Same operation, single data transfer. You have exclamation mark in pre-indexed, right? Here, pre-indexed addressing, you have exclamation mark, meaning base register is updated, right back, right? Same here. Okay. After transfer, after store operation, in this case, STM, right? After store operation, R13 will be updated. Okay. And here, after memory read operation, in this case, be careful. I specified R1 first and R0 next. R1 first, R0 next, but it doesn't matter, right? What does matter? Inside curly bracket, you say R1, R0. That is equal to R0 and R1. CPU cannot differentiate the different orders. Okay? How come? By looking at this, look at this, register list. If you write this code, then bit 0, bit 1, these 2 bits will be set to 1. Compiler, right? Compiler will generate machine code. Okay. Compiler generate machine code, CPU, right? Just read machine code, right? Your machine code, LDM machine code. And read machine code and interpret that machine code and execute it. And in the machine code, you write this code and the last 2 bit, 1, 1. You write this code, last 2 bit, same last 2 bit is 1, 1, or 1, 1. Okay. So then that means CPU cannot differentiate these two, right? Then why do you want to write this code? This one is not good for readability. Probably you want to use this one, right? So look at this. It doesn't matter which order you specify the registers. Okay. So this order R1, R0, R1, R0, R0, R1 doesn't matter. Okay. Same. And one more important thing. Okay. One more important thing. You are listing registers here, right? Registers. Okay. Then this rule applies to multiple data transfer instructions. Very important thing. Row memory location. Row. So in this case, 4 data and 4 data, right? So assume that you are loading these 4 data into here. Okay. Then location 0 go up. So low memory data in low memory location. This is low, lowest, and this one is highest, right? Highest memory location. That is always corresponding to low register number. In this case, we are talking about R3 to R6, right? So that is corresponding to this data in high memory location. That is corresponding to high register number. Always, right? Low, simple rule, right? Low, high, low, high. That rule. Okay. So any questions so far? And one more thing, the last one. So in this case, you want to specify 13 registers here, R0 to R12, right? 13 registers. So R0, R1, R2. I don't want to write this, long list. Okay. So instead, I can use this shortcut dash. Okay. R0 to R12. Okay, that is better. Okay. So you are storing, right? Storing these 13 registers. Storing these 13 registers to memory, right? The first one, LDM. You are reading from this memory location. Okay, reading from and place into these 13 registers. Okay, and you have again exclamation mark, meaning after transfer, R13 will be updated. Okay, that is basic information. And the last thing we have to talk is this suffix. Okay. Base instruction STM, LDM. At the end, you have to specify addressing mode. So why is that, right? Why is that? Let me write example code. LDM instruction. Okay, R13. Let's say exclude. Okay, so I don't have to have. If you want the exclamation mark, but if you don't want, then that's okay. In general, that is used, right? That is used. Exclamation, then let's say R02, R02, R12. Okay, 13 registers. Okay, for simplicity, only 4 registers. R0, 2, R3. CPU, then memory. Then let's say R13. Let's say R13 contains 1000. Okay, 1000, 0, and let's say 1000. Location 1000. 1000 is this. Okay, this data, this one. Okay, you have R0, R13, 1000. Okay, so then load multiple. You want to read from this location, right? So first data is probably okay. Okay, you want to read. So you want to read, from this location. So first data, okay, I know the location. So first data. Then how about the next data? next data is, which one is the next data? This one or this one? What are you talking about? 0, right? It is, address is incrementing like this. So what are you talking about? This plus offset data or minus offset data? It's minus. Which offset data? So it is not clear by looking at this instruction, right? So you have to specify, explicitly say, which one do you want to access, right? That is why they are providing this addressing mode. IA, it is very intuitive. Increment after accessing memory. If you say, okay, this one, Yunjong, can you please read? Read only this one, these two columns.
Addressing mode, there is IA, increment after, IB, increment before, DA, decrement after, DB, decrement before.
Okay, so acronym is very intuitive. Increment after what? After accessing memory. Okay, if you say IA, okay, instruction, then increment R13. R13 is this, right? R13. Increment this address, right? 0 to incrementing, right? Increment this address, okay? 4. After, right? After reading this data, IA, right? Intuitive, right? Increment base register after accessing memory, right? So it goes up like this, okay? Goes up, okay? And also, what else? IB. If you say IB, increment before, right? Before accessing memory, right? What do you mean? What do you mean by that? Then you are not reading. You are not reading this data. You are not reading this data. Increment R13 before, right? Before accessing memory, right? So R13 will be incremented first. Okay, incremented first, then access this. Let me use 1, 2, 3, 4. 1, 2, 3, 4. Okay, increment, then you are reading 2, and place into here 2. Okay, increment before. Okay, and third one, decrement after. IB decrement what? After, right? Decrement after. So the first data you access 1, okay? Access 1 and place into here. That, oh, I'm wrong. Okay. You have to be careful. Low, low, high, high rule. Okay. Low, low, high, high rule. Okay. So R0 to R3. So let me do it again. Okay. Let me do it again. Go back a little bit. Here. 5. Okay. 5, 6 here. Oh, not good. Okay. Okay. A. Okay. A, B, C, D. Okay. Data. Okay. So in case of IA, first, okay, let me go back. Okay, go back. Okay, let me show you the final state in R0, R3. In case of IA, increment after. You read this instruction, this data first, then base register will be incremented. Okay, so you end up having 1, 2, 3, 4. 1, 2, 3, 4. Okay, after executing this instruction. And R13 will be what? R13 after accessing the last data, then pointing this one. So 4, 8, C, 10. So 10, 10. So R13, that is R13, final state. Okay, then, in case of IP, in case of IP, increment before, increment, right? Increment is R13 before you access memory, right? So you increment first and access 2. Okay, so if you execute this one, it's IA, IP, the final state 2, 3, 4, 5. Okay, 2, 3, 4, 5, right? So low, low, high, high rule, right? Low, the data in low memory location is R0, R3 corresponding to low register. Okay. Okay. And the last one, data in high memory location corresponding to high register number. Low, low, high, high. Okay. And then D what? DA, decrement after, decrement after, DA. So the first state, the 1000, right? Decrement after you access this data. Okay. Then what do you expect? You are reading this one, this 4, right? This 4. You are reading this 4. Decrement after, right? Decrement base register after accessing memory. Okay. And then final state is you have to be careful. Low, low, high, high rule, right? CBA1. CBA1. Okay. And then the last one, DB. Decrement before, right? Decrement, right? Decrement is register before you access memory, right? Decrement first. So you end up reading A, B, C, D, these 4. Okay. And low, low, high, high rule, right? So here, D, B case, D, C, B, A, D, C, B, A. Okay. Real confusing, right? But rule is simple. The first important rule is low, low, high, high rule. Low, low, high, high. Okay. And that's it, I think. That's right. So, so how about this example? Oh, okay. One more thing. And if you don't say anything, if you write just LDM R13, R0, R12 like this code, then by default, compiler is assuming you have IA suffix added. That is default. If you don't say anything, okay? Default addressing mode. Let me show you one example. So here, so let me change the code a little bit. So here, I want to read, for example, these 8 data. with one instruction. Then probably at the end, I know the location, then you can use LDM just for fun, right? LDM. What do you want to say? IA first, most obvious one. R0, exclamation mark, this location, right? Then I want to place these 8 data into, for example, R12, R8, for example, like this. Okay, let me execute it. Okay, show you. Okay. So, I think if after graduation, if you want to join, if you join Samsung and Hynix, then, the training, right? First 3 months training for new employees, right? You will study, this ARM programming, right? Same programming, I think. But the quality of, the lecture would be better in this class, right? Don't expect too much in this, newbie training. Okay. So here, F5, right? R0. You have this value, 9E0, and then at that, from the location, you have 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, those data. Then what do you expect? If I press F9, F5, R1 and R8, right? R1 to R8 registers will be populated with 1, 2, 3, 4, 5, 6, 7, 8. And then what? R0 will be what? Exclamation. That is updated, right? So after, what is the location of the last data? This one. So last data, 9FC, right? 9F0, this one, 5, 9F4, 9F8, and C, then A0. So this value, 100, A00 will be here. Okay, so let me press F5 like this. 1, 2, 3, 4, 8, then A00, A00, this location. Okay, and one more thing just for fun. This one, because this one is a little bit curious, right? Low, low, high, high rule. In case of decrement after or decrement before, right? Decrement after, before, right? So let me write one more code. So from this location, right? So how about this? Okay, let me place. At the end, R0 is updated. Which one? LDM, load multiple, new location, decrement, right? Decrement. Good. LDM, D, decrement before, I don't know. Let me put everything R0. Then place into R. I have to be careful, right? It's 9, 9, 2, R 12, 9, 10, 11, 12. How about 4? 4 data only. Right? So that is decrement. Right? Okay. Decrement. Okay. So okay. So if you do this, decrement before. Okay, then debug. Deregister. Okay. Press F5. Press F5. Then let's think together. R0 register has A00, right? A00. Decrement before, right? Decrement before. Before accessing memory, decrement. That means what? That means you are accessing 8, 7, 6, 5, 4 data, 5, 6, 7, 8. Right? Decrement, right? Decrement before accessing memory, right? Decrement. So 4 data. Okay, so 9, 6, 7, 8. That will be placed into what? Where? 9, 5, 6, 7, 8. 9 first, right? Low, high rule. 5 to R9 and 8 to R12, right? So let me press F5, right? Low, high rule, right? 5, R9, okay, 8, R12, right? Okay, any question about this? All right, let's move on. Okay, the stack operation. This one is also important. This one, Jinu, can you please?
Multiple data transfer instructions are used to load and store multiple words or data from to main memory.
Okay. ARM compiler, right? We now know everything about load multiple instructions. We studied this one, STM, and suffix, right? 4 different suffix, 4 store multiple, and 4 different suffix for load multiple, right? And in addition to the instructions we studied, ARM, I would say compiler is providing these pseudo instructions. Same instruction, actually. These two are the same instruction. FA, IB, EA, different suffix, right? Name is different. FA means what? Full ascending. EA means empty ascending. Okay, F means full. E means empty. So those instructions are provided for stack operation. Stack, right? Stack is used all the time when you run your high level program, right? And assembly program also. Stack is simply memory area you reserved, right? Okay, 1 kilobyte this memory. I want to use this 1 kilobyte as a stack. Stack is what? To backup. To backup, because we have only 16 registers, right? Sometimes you want to backup some registers to memory because you have only small number of registers. Okay, to make room for other data, place other data, then do some processing. So before that, you want to back up those registers. That is called push operation. Push, and opposite is pop operation. Push and pop. Right? So location 0. Okay, push and pop. And stack is used all the time, so frequently, right? ARM is providing those pseudo instructions, okay, for stack operation to make your life easier. It is for your convenience, right? So why they are providing this instruction? Let me explain, right? let me explain the default stack. Default stack is R0, R13. R13 is different name is stack pointer, right? Stack pointer. So here you have to initialize this register before you use a stack. You have to re-initialize this register. So let's assume in this case, the location, there is 1 kilobyte stack and 1 byte above. 1 byte above. I'm drawing very carefully. 1 byte above. Okay, 0 to incrementing. Okay, let's assume their location is 1000. Then you have to initialize that register to 1000 by program. Okay, and then because we reserved this area as a stack, if you want to back up some registers, okay, I want to back up these registers to these 4 registers. 4 registers to here 4, right? 4. Okay, 4 registers backup, right? Then what do you have to do? You have to decrement, right? Decrement. Because this R13 stack pointer is pointing 1 byte above, right? One above actual stack area. You have to decrement the decrement, right? Spelling. Decrement first, then store. Decrement first, then store. Right? Decrement, then push. Right? Decrement. Okay. So in this case, because we are using in the stack operation, we are using full stack, full or empty. We use that terminology. Stack is full. Stack is empty. We use that terminology, right? That is why ARM is using that terminology, full stack, empty stack. Okay. So in this particular example, the location, this location stack pointer is pointing. We think of it as full, right? This is not stack area. So we think of it as full. Okay, the location is full. It is occupied already. So to push this data, you have to decrement first. So in this case, full, suffix, full, stack is full. So decrement D, decrement. Full decrement stack pointer first to push, right? So in this case, we have to use STM. Okay, here. STM store multiple full descending FD. We have to use that instruction. Okay. Then at the end, right? At the end of pushing these 4 registers to the stack, the final state is this one. Stack pointer is pointing now their location. Right? 4 decremented. So if I write the address, decrement this number by 4. Hex number. What is that? Kuyun. You are from math department, right? So location. Confusing, right? -4. What is the number? Location. 100 minus 4. Kuyun, come on. 100 minus 4. What is the number?
0FFC, I think.
FFC. Yes, correct. FFC. Okay, let me use FFC, right? FFC, F8, F4, then FF0 location. Stack pointer is pointing that location. Stack pointer contains FF0. So then, if you want to pop opposite, right? Store. If you want to pop, okay, push. If you want to pop, then what instruction do you want to use? You can simply use, because when you push, you use this suffix. Then when you pop, use the same suffix, like LDM, FD. Same suffix, FD and FD. Right? Full descending, right? So in this way, programming is, simpler. Assembly programming is simpler. When you push in the first code, then you do push. Okay, you are safe to use those registers. Some program, right? Push, then do your job, then pop function, your function, foo. Right? You push using STMFD. Then when you pop, use LDMFD. Simply use. Don't worry about increment after, increment before, or decrement after, decrement before. It is confusing. Okay, so just use this terminology. Full stack is full stack, or empty stack. Okay, then think about that. This FD is corresponding to which one? It's which suffix? Let's think. Okay, stack pointer is pointing this location. So STM, you have to decrement first, right? Decrement before, right? Before you access memory, you have to decrement before DB. If you want to use, one of these suffix. So that is corresponding to, that is equal to STMDB. Look at that table. STMDB, full descending, store multiple, decrement before. Okay, how about this? Load full descending. Okay, that is equivalent to what? Load multiple. We want to use one of these, one of these four, right? Think about that. That is, occupied already. So you have to read first. Okay, you have to read, then increment. Increment after, right? Read this data first, then increment next. So IA, right? FD is corresponding to IA. Okay. So assume that, instead here, if you want to use, one of these four, that's okay. But look at this, STM, which one? DB, right? DB, here, LDM, IA. Very confused, right? DB. Okay, then you have to think twice. Decrement before, right? Decrement before, okay? Stack operation, you have to think, okay? Before accessing memory, I have decrement, okay? Okay, you have to think, twice or more, right? And if you use IA, when you pop, then IA, right? Okay, the location, stack pointer is pointing, is taken, already populated. Okay, I have to read first, then increment. So it is confusing if you use DB in IA, because you have to think twice or more. Okay, not that intuitive. Sometimes you make mistakes. Okay, that is why ARM recommends you to use that suffix for stack operation. When you push, you use FD, then at the end you use the same suffix. Don't think about this IA. It's confusing stuff. Yunjong, yes. Yunjong, yeah, Yunjong's question. Yunjong's question. When you ask, probably you can ask to everyone, right? Yunjong's question is this one. Everyone. That's okay. Don't be shy. Yeah, it's okay. You are here to learn, right? That is Yunjong's question. Right, the same. Do you have example? Okay, so that example. So you can do this, right? R12 first, right? And R9 next. Right? That's okay. Same operation. Okay, let me. Bad range. Okay, when you probably you have to. I don't know, but probably that is illegal. In this case, you have to. I don't know. R10 like this. What does it say? Not ascending order. Probably, okay. So compiler may be complaining. You have to use, better to use, I think, warning, right? So let me show you the machine code. Check out this, okay? That instruction, then same instruction. The important thing is machine code, right? This machine code. And then machine code. Same machine code, right? 1E00. Same 1E00. Same machine code means what? CPU cannot differentiate these two. Same operation. So machine code is important, right? This one. You understand? Okay, this one. Register list. Here. In the machine code, right? The low 16-bit register list. Okay, 1E00. So what is 1E00 in binary? One E00 in binary. One is 1, right? E, but 1110. So 00, right? 0000. So this one is R0, right? And R1, R15. So 14, 13, 12, 11, 10, 9. Okay, four registers. Okay. So my recommendation is, play with this IDE, write some code. Okay, if you are curious or confusing, then write some code and compare the machine code, right? In this machine code. Okay, then you figure, okay, these two are the same. Then why do you want to use this code, right? This code. Because it is confusing, right? So you don't have to list all 4 registers. Descending order, confusing, right? Descending order, right? So this one is more readable. Okay, more. So I don't want to use, even though these two are same instructions. Okay, I don't want to use this one for readability reason. Okay, I want to use this one. Any other questions? Okay, one more thing. Swap instruction. Okay, swap instruction. This one. Can you please? Which one? Who? Munchon. Munchon. Can you please? Are you there? Okay, Gyeongnam, can you please?
SWP swaps the contents of memory with the contents of a register. It is a special case of a row store instruction. It performs a swap automatically, meaning that it does not release the bus until it is done with the read and the write. It is useful to implement semaphores and mutual exclusion in an OS.
Okay, thanks. Swap instruction. Okay, swap instruction is, you cannot use swap instruction. It is deprecated in version 7. Okay, Cortex A9. Cortex A9 is based on ARM version 7, right? So if you use swap here, SWP swap R0, R1, R2, for example, then compiler will complaining, say something, right? Problem. Okay, look, error, deprecated. Okay, you cannot use swap instruction. Okay, swap instruction. Then why do I want to bring up this swap instruction and explain? Because it is very intuitive instruction. Very, it is good example of instructions to explain the issue. Okay, I want to address. So why do you need this kind of instruction swap? It's very special instruction. Swap R0, R1, R2. That instruction is doing two memory accesses. First one, swap, right? CPU, memory. R0, R1. Okay, you want to swap. Swap what? So here, memory location. Let's say you have some data 5. Okay, so R2, 1000. R2, 1000. So you want to read. Okay, memory read. So it is LDR, operation, memory read operation. So read from this location, place into here, R0. So 5. So 5. Okay, then store operation, memory write operation. This data, let's say you have 4, that will be stored like this. Swap, you are swapping, right? So memory read and memory write. So two memory accesses. The important thing is that is automatically performed. So not automatic, atomically. Atomically performed, atomically. Not automatically, atomically, right? You cannot separate these two. Okay, you cannot separate these two. What do you mean by that? So you have to understand little, you have to know little detail of hardware accessing, CPU accessing main memory, right? So CPU, you have main memory. Okay. Then to access main memory, you have to go through this connection called bus. Okay. This memory. Then probably you have another CPU right next to multiprocessor system, right? Like this. Okay. So to think about this memory read LDR, STR instruction to access, to read from memory. These two guys sharing this common connection called bus. Okay, common connection. So to read, to access, read or write, right? Read or write, right? To access, for CPU to access memory, what do you have to do? What if these two guys are requesting memory access at the same time? Two guys, okay, I want to access memory, right? This guy is is about to execute LDR. This guy also about to execute LDR. Two guys are requesting memory access at the same time. So problem, right? One connection, two guys are competing. Two requests cannot be serviced at the same time. So one at a time. This guy's request first, or this guy's request next, or vice versa. This one first, this one next. Someone should do some arbitration. So in general, right, there is a hardware device called arbiter in multiprocessor system. Arbiter, hardware component, right? So that guy is doing request, okay, request. Okay, that guy also generating. We have connection, physical connection, request. Then and grant this connection, grant. Okay, you got grant. You are granted. You are allowed to access memory. So that also grant connection. So two guys, in this case, two CPUs are requesting to arbiter. Okay, I need to access main memory. Then who should go first? Okay, this guy, arbiter, is doing arbitration. Okay, and make that decision. Okay. So then, okay, 46. Okay, let me finish this because I raised this issue. Then if you execute the LDR and STR next, then probably LDR instruction, STR instruction, LDR, STR. Okay, so that guy is doing memory read. Okay, so order, time, right? One probably then arbitration for fair arbitration. Arbiter should grant next CPU number 0, CPU number 1, okay, 2. You go first, and this one next, probably 3 and 4. This order 1, 2, 3, 4. Probably arbiter make the decision. So LDR instruction, right? LDR instruction got executed first, and this LDR instruction got executed next. Then store instruction next, and then next, finally. Okay. Then we have some problem if you want to access lock variable in memory. Okay. There are some variable in this memory. Okay. Think about that. You want to two people are sharing one printer. Two people, right? Two people want to access, common, the printer shared by these two. Then one at a time, right? One guy send, document to printer. Then at the end, after one guy use that printer, the next guy can use it, right? You cannot interrupt that process. So printer access. Okay, so time. Okay, probably it takes some time. So let me continue next time. Okay, probably I cannot finish it in 5 minutes, probably. So better to explain next time. So please read this issue. Semaphore, mutex, mutual exclusion, that issue in operating system. Okay, you want to access hardware resource shared by multiple processes, multiple CPUs, multiple programs. Then what do you have to do? Okay, one entity, one printer is shared by multiple guys. Then what kind of mechanism do you have to implement to make it work properly? Okay, one guy send printing job, and then some other guy can send printing job. You cannot interrupt between these two. In the middle of one guy is printing his document in the middle, A4 paper, right? In the middle of printing, halfway. Then you got interrupted and printing your document. It doesn't make sense, right? It mixed up, right? It messed up. So think about that issue, then read this semaphore, then we can Next time continue. Okay, any question before closing up? Okay, that is it. See you next time. Bye. Okay, thanks.